Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 1, Lesson number 8, Additional Properties of Lines. Now this is very important because there are going to be a lot of different things that are going to arise in the various units of this course that we're going to see today. Although today's lesson is going to be a little bit unique. You're not going to be like learning a piece of geometric terminology and then applying it in some algebra problem or doing any kind of constructions or anything like that. You will have to do a little bit of drawing, but mainly I'd like you to discuss things with other kids in groups, or if you're just watching this video on your own, make sure that you're thinking hard and playing around with these problems, and then I'll kind of try to have that discussion with you. Let's jump right into it. All right. Today is all about what are called axioms, also known as postulates. You see, 2,500 years ago roughly, Euclid wrote his seminal work called The Elements. And in that, he lays out assumptions that we can't prove. Things that we just assume are true from everyday life and experience. And then using those axioms or postulates, Euclid then taught us how to build up a system of geometric thought that then could prove beyond any reasonable doubt, using pure logic, all the rest of what we know in geometry. And today what we're going to be doing is looking at some axioms and postulates that apply to lines. But first, let me read off the definition of what an axiom/postulate is. Axiom or postulate: a mathematical statement that is assumed to be true without proof. Without proof. All additional theorems are built on axioms and reasoning. A good example of an axiom that you've seen before, right, comes from algebra. Like this: when equals are added to equals, the result are equal. You saw that back in Algebra 1 when you were solving equations and trying to justify the steps that you were using. All right, if I have 3 equals 3 and I add 2 to both sides, I get 5 equals 5, right? It's a fundamental thing that we assume is true, all right, without really any way to prove it other than just from common experience. Hey, I got 3 rocks equals 3 rocks. I put 2 more on both sides. It's both equal to 5, right? It's not really a proof, okay? Let's get into the lesson though. Gotta see where we're going with all this, because it can be a little bit weird. All right. So exercise 1 and exercise 2, that's basically all we have today, but there's lots of then sub-exercises in them. So let's take a look at what exercise 1 asks us to do. All right, for each of the following axioms about straight lines, try to draw a picture to disprove the fact, right? And again, each one of these things is an axiom, which means it's true to the best of our knowledge, so we're going to call it a fact, all right, and to discuss. Keep in mind that we're talking about straight lines that extend forever in 2 directions, okay, that extend forever in 2 directions. So one of the first assumptions that Euclid makes in his Elements is what we have in letter A. Through any 2 points, only one straight line can be drawn. I can't draw more than one straight line through any 2 points. Play around with this a little bit. Take out your ruler, draw freehand, do various things, but kind of play around with this a bit. All right. Again, what's the purpose of what we're doing today? The purpose of what we're really doing today is just understanding these basic assumptions. Now the plain fact is, if I kind of come here and I grab my line tool, okay, come out here and I draw this, and of course I could extend it sort of on both sides. That was lovely and well done. I claim that's it. That's the only one I can get. And again, the fact is, if I go back and I try to do anything else, any other kind of line that isn't this one, put that away, right? If I try to connect A to B in any other way that doesn't lie right on top of that, I end up having to curve, to go around, right? I can't get from A to B, along a straight line segment, except for along that line segment. That's it. Right? A fundamental assumption. No way to really prove it, except we just accept it as being true. Whatever that means. All right, let's take a look at the next one. Another assumption that Euclid makes is that the shortest distance between any 2 points is comprised of the length of the straight line segment connecting them. Right, oftentimes we'll talk about the distance between 2 points, but of course that implies a path and the length of a path, right? And what Euclid assumed, and what most of us believe is true, is that the shortest distance between any 2 points is a straight line. So play around with that a little bit and think about why, at least intuitively, that seems to be true. All right, let's talk about it a little bit. Well, again, kind of going back and grabbing my line. All right. I'm claiming that this is going to be the shortest distance. If I measure that length, piece of string, take it out, put it up to my ruler, my claim is that's going to be the shortest one. And again, think about it for a moment, right? If we then tried to connect A and B with anything else, right, besides that straight line segment, intuitively we just get this sense that if I took that piece of string, right, and I stretched it out, right, that it would then end up being longer than the straight line segment that I originally used to connect A to B. And yet again, how do we actually prove that? How do we know that we wouldn't be able to go faster or a shorter distance from A to B by some kind of cool curve that isn't just a straight line? But we're going to assume that's the case. The shortest distance between any 2 points is the length of a line segment that connects them. Let's take a look at another one. All right, this one's kind of cool. Letter C says 2 different lines will either share, intersect at 1 point. So again, let me say that a little bit better. Will share 1 point, or share none at all. Okay, known as parallel lines. Any 2 lines that share 2 or more points are the same line. Okay, so let's make sure of this, right? If we have 2 lines that are different, okay, because you can have 2 lines that are the same line, you know, maybe you just call them different things. But if you have 2 lines that are different, then there's only one of 2 scenarios. Either they intersect once, or they don't intersect at all and are therefore called parallel. So play around a little bit with this. Draw pictures, illustrate what you have. Try to illustrate 2 non-lines that maybe intersect more than once, but play around with this idea. All right, let's go through it. So again, I'm not going to grab my line tool here, but you know, if I've got this one line, and then I've got this other line, I seem to have a little lag right now on my board, but if I have it right, they're only intersecting at that 1 point. On the other hand, I could have a line like this, and another line like this, with a 1 second delay. Now I didn't draw these 2 lines perfectly parallel. They probably would intersect eventually if they were extended forever up to here. But give me a little bit of leeway. Those 2 lines don't intersect at all. The only way that we can get curves that intersect more than once, right, 0 times, is if they aren't lines. So if I had a line, awesome, and I had another curve like this, they would have to intersect twice, right? And that's fine, but then that's not a straight line, all right? So straight lines either don't intersect at all or intersect once, or intersect an infinite number of times, but that's only if they're the same line. All right, let's take a look at another one. Okay, letter D. Let me read through it for you. Through any point not on a given line, there is exactly 1 line that can be drawn parallel to the given line. Okay? This is an amazingly interesting postulate or axiom by Euclid. It was one of his most controversial ones. And again, it basically, make sure you understand this. I've got a line. I've got a point that doesn't lie on the line. And what Euclid said was that there's absolutely just one line that will pass through A and will be parallel to this line. A lot of geometers later on, much later than Euclid, we're talking like late 1800s, started to toy around with this assumption a bit, and it gave rise to all sorts of cool different types of geometry that had kind of exotic names like hyperbolic geometry, okay? But for now, just play around with that. See if you can draw more than one line passing through A that's also parallel to that. See what you can do. All right. Well, I'm gonna actually go back to my line tool in the hope that maybe this will become a little bit more responsive, but we'll see. All right. So I've got my line, and oh, there it is. Well, now it's just working fine, right? Okay. So there I've got a line, kind of, that passes through A and looks like it's parallel to this line. The plain fact is, if I try to draw another one, right? If I try to do something like this, any other line that passes through A will no longer be parallel to this line. It'll intersect it somewhere, whether it's down there, well, that works a little bit better, or there. This is an amazingly important axiom. We're going to actually see it come up in our reasoning in Unit 2 a fair amount, where we will know that a line is parallel to a given line and passes through a point, and we'll need to have that argument that there's only one line that can be made like that, okay? All right, let's move on to a whole nother set of axioms or postulates, all right? Exercise 1. Now, there's additional ones that, again, when we present them to you, they might seem really obvious, and if they do, that's a good thing. Because axioms should be rather obvious. I don't know that that last one was, the parallel postulate. I don't know that that was really obvious. But most of these will be. So let's jump into exercise number 2. Okay? Kind of the same directions as before. For each of the following axioms, try to draw a picture to disprove the fact. Discuss. Keep in mind that we're talking about straight lines that extend forever in two directions. So let's take a look at letter A immediately. It says, through any point on a given line, exactly one line can be drawn perpendicular to the given line. All right. Again, this is an important axiom. I've got a line, and I've got point A lying on that line. And what this axiom says is that there's one and only one line that passes through A and is perpendicular to this line. Interestingly enough, this is actually sort of what's called a corollary to an axiom we saw previously, in a previous lesson that is, which is that there's only one angle bisector. If you think about it, this is really a 180-degree angle with a vertex at A, right? And what I'm saying is I can only bisect that with one line. Why don't you go ahead and play around with it a bit? All right, well, let's take a look. Again, what are we really doing here? We're playing, we're drawing pictures, stuff like that. All right. If I've got this particular diagram, let me go in red, right, and I draw, oh, that's fascinating. That looks like I was drawing a river on here or something. I have no idea what just happened there. Let me actually maybe go with my line tool, because I don't know. That seems a little bit better. We'll just go with that. There is only one line, and I don't think that's it, but close enough, that's perpendicular to this one. Any other line that I should draw right now, right, any other line I draw through A, that angle is not going to be a 90-degree angle, okay? Only one line that goes through A will be perpendicular to the line that contains A. Let's take a look at another one that seems very, very similar, right? Letter B, through any point not on a given line, exactly one line can be drawn perpendicular to the given line. Oh, given line, given point, not on line. All this terminology. Again, make sure that you can read through it. I know reading can be a challenge sometimes. Make sure that you're careful about it. All we're saying is this. If I've got this line and I've got this point that's not on this line, then I can only draw one line that passes through the point and is also perpendicular to that line. A little different from the last one, right? The last one was that the point was actually on the line. Here, the point isn't on the line. So play around with that one a bit. Yeah? Let's go through it, okay? So, well, again, the idea here, I think we still have the line tool on, we do, is that there I've tried my best to draw a perpendicular line that goes through A that's perpendicular to this. Any other line that I draw through A, any other one, can't be perpendicular to this one, right? And again, we can kind of sense that by drawing some other lines in, right? There's no other line that will now make a 90-degree angle with this one, okay? Just that first one that I drew. Let's take a look at another axiom. Now, this one I kind of love. In geometry, we sort of want to make sure, as is the case in all of math, that we really have things defined as succinctly as we can. So let's take a look at this. A given line separates the plane into two halves. Now this is cool. The plane is this idea of a flat surface that we're working on all year long until we get to three-dimensional geometry. The plane extends forever but is flat, right? We're living in that. And this basic axiom says, or starts off by saying, if I draw a line in the plane that extends forever, then it cuts it into two distinct halves, right? And then the first axiom is any point in the plane lies in only one of the half planes or on the line. In other words, I don't have a point that lies in one half plane and the other one at the same time. It either lies in one plane, one half plane, the other half plane, or on the line itself. This one I don't think you need to pause a lot to think about. The plain fact is, if I have this point, right, then it's on this side of the line. If I have this point, well, it's on this side of the line. And I have a point like this, and it's right on the line. And again, keep in mind, right, if you're getting cute about it and saying, well, what about this point way out here? Again, keep in mind, right, that this line extends forever in two directions, so we're still on that side. And yet, how would we know? How would we know whether or not 2 points were on opposite sides of a line? This is really kind of cool. Take a look at the last axiom of the day. I'm going to extend the page a little bit. That way we've got a little bit more room to work with here. All right. 2 points are on opposite halves if and only if the line segment connecting them, intersects the given line. All right, now again you might say to yourself, well, it's pretty obvious that A and B are on opposite sides of the line, or are in two different half planes, whereas B and C aren't, right? But this gives you a wonderful, wonderful test of it, right? Which is, if I connect A and B with what's supposed to look like a straight line, but kind of doesn't, right? It intersects that line. On the other hand, if I connect B to C, right, then that line segment doesn't intersect that line, and therefore they're on the same side of the half plane, right? Again, the idea of the plane is very, very important. It extends forever in a flat way in all directions, right? And if I slap a line down on that plane, it's going to divide it into two distinct halves. All right, let's wrap this up. Okay, not an overly long lesson today, and probably a little bit on the weird side, right? What we wanted to make sure is that before we move on to Unit 2, which is coming right up, before we move on to Unit 2, we really understand basic terminology, which we've seen in other lessons, and we also understand some of the assumptions on which geometry is built, right? Especially important today was that parallel postulate, i.e. if we have a line and a point not on the line, then there's only one parallel line that can be drawn through it, okay? But there's many of the other things that we saw today that we'll be using as well in future lessons. For now, I want to thank you for joining me for another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.